Hi everyone. Today we're going to be covering section 6.3, which is about definite integrals and antiderivatives. So hopefully by now this concept of integral has become pretty clear to us. So we know when we're finding the value of an integral, what we're really doing is finding the area between a curve and the x-axis. And so far we've been using we've had a couple methods. We used rectangles and trapezoids to approximate that area, and then for some specific curves we were able to use geometry formulas. But today we're going to learn how to find the value of of an integral exactly using what we call antiderivatives. So, for a quick review, hopefully this is all, we can call this up really easily. We know the derivative is the slope of a tangent line or a line at a specific point. We also know the derivative is the instantaneous rate of change. Okay, and it's been a while since we worked with this, but we know the derivative of position is velocity, and the derivative of velocity is acceleration. Now, when we're talking about the integral, we know that's the area trapped between a curve and the x-axis. It can be approximated using, let's do LRAM, RRAM, MRAM, and the trapezoidal rule. It can be computed exactly using geometry formulas. Okay, now we talked about integration being able to take us backwards. So now if I take the integral of acceleration, that's going to take me back to velocity. And likewise, if I integrate a velocity function, what we're actually going to get is position. Now, today I said we're going to be using what we call antiderivatives, right? Basically being able to work backwards. But in order to be able to do that, we need to be very good at going forwards or doing our derivatives. So we are going to do a very quick review of the derivative rules we have so far. And again, at this point, if these are not automatic, this is when you need to have these be automatic. So we'll be working, making some flashcards and things, making sure that at this point we really don't have to think about these derivatives. So let's go ahead and run through. The first one is our power rule. So if I have the derivative with respect to x of x to the n, we know that's just n times x to the n minus 1. And number 2, we're going to let k be a constant. So if I take the derivative of a constant, we know that's just 0. Derivative of sine x is cosine of x. And again, these should be this quick for you to come up with. Derivative of cosecant of x is negative cosecant x cotangent x. Derivative of cosine x is negative sine x. Remember, all those cos are going to be negative. Derivative of secant x is secant x tangent x. Derivative of tangent is secant squared of x. Cotangent is negative cosecant squared of x. Derivative of e to the x is e to the x. Derivative of a to the x is a to the x times the natural log of a. Derivative of natural log of x is 1 over x. Log base a of x is 1 over x times the natural log of a. Now, derivative of inverse sine of x, that's going to be 1 over the square root of 1 minus x squared. Derivative of inverse cosine is the same, but negative, so negative 1 over the square root of 1 minus x squared. Derivative of inverse secant is 1 over the absolute value of x times the square root of x squared minus 1. Cosecant, just the opposite of that. Inverse tangent is 1 over 1 plus x squared. And so the derivative with respect to x of the inverse cotangent of x is negative 1 over 1 plus x squared. And obviously in all these cases, if our argument here is anything other than just x, we know the chain rule will apply. So that's a quick run through of our derivative rules. So now we're going to really start looking at these antiderivatives. Okay, so using antiderivatives to calculate an integral exactly. So here's the idea. If f of x is the antiderivative of f of x, then the integral from a to b of f of x dx is, here's the notation. We're going to take our antiderivative, f of x, and we're going to evaluate that over this interval from a to b. What that really means is we're taking our antiderivative, we're evaluating it at b, and we're subtracting the value of that antiderivative at a. So let's take a quick look at what this would look like. So just so we're clear on the notation, obviously here in my integral, here's my f of x. Now, my antiderivative for x squared, and we'll look at why this works in a minute, but I know my antiderivative, what we called f of x, is going to be x cubed over 3. So now we said this integral is equal to our antiderivative, so x cubed over 3, and I evaluate that from 0 to 2. So what that really means is I take my antiderivative and I evaluate it at 2, so I have 2 cubed over 3. And then I'm going to take my antiderivative and evaluate it when x equals 0, so minus 0 cubed over 3. So what we get then for our antiderivative is 8/3. So what that tells me is that if I take my function x squared over the interval from 0 to 2, the area trapped between that curve and the x-axis is 8/3. And that's an exact area, so now we don't have to rely on our approximations anymore. So on this page, all we're going to do now is look at these values and go backwards. So if we're integrating these functions, we're going to use our knowledge of derivatives to figure out what the antiderivative is. So here we go. For power rule, we know when we were differentiating, we multiplied by the exponent and then we subtracted 1 from the exponent. So here, we're going to go ahead and we're going to do the opposite. So for power rule now, we're going to take x, we're going to add 1 to that exponent, and then we're going to divide by n plus 1. So if we go back up to our example here we had x squared. So what I did was I added 1 to my exponent, 2 plus 1 gave me 3, and then I divided by that new exponent. And you can check easily by differentiating that we did it correctly. If I have 1/3 x cubed, I'm going to multiply by 3 and subtract 1 from the exponent, I do get back to x squared. So it's easy to check that we did it correctly. Now, when it's x to the negative 1, we have to be really careful here. Because if we tried to use our power rule and we add 1, we would get x to the 0, which is just 1. So we have to be careful and realize that this is the integral of 1 over x dx. And now we should realize, well, I know 1 over x was the derivative of natural log, so my antiderivative is the natural log of x. So we have to be careful when this is negative 1. We can't use the power formula here. We have to recognize that that antiderivative is natural log of x. Okay, so let's continue on here. If I have the integral of cosine x dx, I know cosine x is the derivative of sine of x. So my antiderivative is sine of x. Now, when I take the integral of sine of x dx, I have to be very careful because I know that sine is going to be a derivative of cosine of x. But now if I differentiate cosine of x, I get negative sign. Since this is a positive sign, it means my antiderivative must be negative. So we're going to have to be really careful with signs when we're integrating. Secant squared of x, my antiderivative is tangent of x. Cosecant squared, again, we have to be very careful here. We know that's cotangent of x, but again, since this is positive, this must be a negative cotangent of x. Here, the integral of secant x tangent x is secant of x. And cosecant x cotangent of x is negative cosecant of x. Okay, then we have our exponential and logarithmic. First one up is e to the x, which is very straightforward. We know that's just e to the x. My integral of a to the x dx. Now, here's where we have to be a little bit careful. I'm going to kind of take an aside here. I know that if I had the integral of a to the x times the natural log of a dx, that I recognize. I know the antiderivative of a to the x times the natural log of a is just a to the x. However, here, I'm missing that natural log of a. So my antiderivative is going to be a to the x divided by that constant natural log of a. Okay, the integral of 1 over x dx is natural log of x. Integral of 1 over x ln a, hopefully I recognize that that is the derivative of log base a of x. And then again, a couple inverse trig functions. 1 over 1 plus x squared, that is the derivative of my inverse tangent of x. Here I recognize that this is the derivative of my inverse secant of x. And then this one is my inverse sine of x. So again, this is where we have a lot of work to do in just getting these things to be automatic. So when I see these integrals, I can automatically find their antiderivative. So the last thing we're going to do for today is just go over some examples of some problems using antiderivatives. And again, these should be ones that we recognize right away or can easily anti-differentiate using our power rule. So here we go. The first thing I'm always doing is looking for the antiderivative of my function. In this case, I know the antiderivative of secant squared of x is tangent of x. And I'm going to evaluate that over the interval from pi over 6 to pi over 4. And you'll see a lot of times instead of using those whole brackets, I'll just use this line and indicate my interval. So again, we said that means I'm going to evaluate tangent of pi over 4 minus tangent of pi over 6. So I know tangent of pi over 4 is 1. Tangent of pi over 6 would be 1 over root 3. And for our purposes, since I really want to enforce doing these without a calculator, we're just going to leave our answer exact. Okay, so number 2 is another trig one. Here again, we have to be a little careful. Now, one of the properties here of integrals is that we can move that 2 in front of the integral. But really, I know that's not going to matter here, so I'm going to put my 2. Now, my antiderivative for sine, I know, is negative cosine of x. Because again, if I were to differentiate this, I would have negative 2 times the derivative of cosine is a negative sine of x. So those negatives would cancel and give me a positive 2 sine of x. So I have negative 2 times the cosine of x, and I'm going to evaluate that from pi over 2, sorry about my fingers being in the way here, to 5 pi over 6. So now I have negative 2 times the cosine of 5 pi over, whoops, I don't know why I'm putting it up there, cosine of 5 pi over 6 minus negative 2 times the cosine of pi over 2. So thinking back on our unit circle here, I have negative 2. The cosine of 5 pi over 6 is going to be negative root 3 over 2. And then minus a negative 2. Cosine of pi over 2 is just 0. So then I just get a positive root 3. All right, the next one. Here we see our exponential, and this is actually a nice, easy one. I know the antiderivative of e to the x is just e to the x. So I have 2 times e to the x evaluated from negative 2 to 0. Now, what we can do when I have this 2, here I just kept that 2 with both of my terms. We could factor out the 2 and then just evaluate the e to the x at these limits of integration. So I have 2 times e to the 0 minus e to the negative 2. Just want to show you both ways of dealing with that there. So 2 e to the 0 we know is 1. So I have 1 minus 1 over e squared. And so my answer is just going to be 2 minus 2 over e squared. And again, I want us to first do this without a calculator, get very comfortable with these calculations, so we'll just leave that answer as is. All right, next we're going to do a pretty basic power rule formula here. So I'm going to anti-differentiate both of these terms. So for x squared, or 2x, we know really our exponent is 1. So what I'm going to do is add 1 to that exponent, which is going to give me x squared. And then I'm going to divide by 2. However, since there was a 2 in front, dividing 2 just cancels it, and my derivative, or antiderivative, is x squared. Again, if you were to differentiate that, you would get 2x, which is what we're trying to get to. Now, my next term is just a constant, so all we need to do is add an x. So now we've got our antiderivative, x squared minus 2x. We're going to evaluate that from 0 to 3. So now we just have to be careful because I have 2 terms in my antiderivative. So when I evaluate it, I have now 3 squared minus 2 times 3. And I'm going to subtract the value of that at 0. Well, I know, obviously, if I plug in 0, I'm just going to get 0 there. So now I have 9 minus 6, and my value is 3. I'm going to skip number 5 because that's the power rule again. Let's look at number 6. Again, hopefully this should jump out at us right away. All this is the antiderivative is the inverse tangent of x. All right, so my antiderivative is the inverse tangent of x, and I'm evaluating that from 1 to root 3. So I have inverse tangent of root 3 minus the inverse tangent of 1. So I know this value is going to be pi over 3, and inverse tangent of 1 is just pi over 4. And again, I would always recommend, if you're doing your homework, doing it by hand and getting an exact answer first, but you can always go back and check by plugging it into your calculator to make sure you have the correct answer. All right, 2 more examples quickly, and then that'll be enough for today. Now, for number 7, here I said we had to be careful. This is our tricky one. And it may be a little hard to recognize here, but if we realize this is just the integral from 1 to 4 of 4 times 1 over x dx, hopefully we recognize 1 over x, its antiderivative is natural log of x. So what we have is 4 times the natural log of x, excuse me, and we're going to evaluate that from 1 to 4. So now to calculate, I have 4 times the natural log of 1 minus 4 times the natural log of 4. Well, the natural log of 1, hopefully we don't have to think about that. We should recognize that is just 0. So this term is going to cancel out, and I'm going to get negative 4 times the natural log of 4. Okay, sorry guys, I actually did this backwards. I had to be careful here with my order. So this should have actually been 4 times the natural log of 4 minus 4 times the natural log of 1. This term is 0, so I should get a positive 4 times the natural log of 4. Sorry about that. All right, one more and then we'll be done for today. All right, now here, we have to be careful here. I'm going to rewrite this to make this a little easier to deal with. So I'm going to have the integral from negative 4 to negative 1. This is really negative 5x to the negative 3 dx. I think rewriting it helps us because now we can just use our power formula. So I'm going to take my my variable, and I have my exponent is negative 3. I know I need to add 1 to that, so I'm going to have x to the negative 2. I have my negative 5 out front. I'm going to divide by that new exponent. So we have negative 5x to the negative 2 over negative 2. That's our antiderivative. And now we're going to evaluate that from negative 4 to negative 1. So first thing I'm going to do, I'm just going to cancel these out to make that positive. And I actually think this is the same as 5 over 2x squared. And again, I'm evaluating from negative 4 to negative 1. So now I have 5 over 2 times a negative 1 squared, so that's just going to be 5 halves, minus 5 over 2 times a negative 4 squared. A negative 4 squared is going to give us a positive 16, times 2 is 32. So I'm just going to get like denominators here. So if I multiply by 16, I'm going to get 80 over 32 minus 5 over 32. And so we're going to get a value of 75 over 32. All right, so I know that is a lot. We're going to do a lot of practice with this tomorrow. And again, it's just going to be practice and making this become more automatic. So I will see you in class tomorrow.